Okay, hello everyone. Welcome to the GISS Sea Level Rise seminar. We're very glad to have Dr. Paul Winberry with us. He's a research scientist at Central Washington University, where he focuses on glaciology and polar seismology. He has over 20 years of experience in geophysical and remote sensing analysis of glaciated regions, and he's been to on 16 Antarctic expeditions. Dr. Winberry earned his PhD and master's degree in geoscience from the Pennsylvania State University and his bachelor's degree in geoscience from the University of North Carolina. And he will be speaking today about insights into Antarctic glacier calving and subglacial hydrology from geophysics.
Okay, great. I'll share my screen. Okay, going to start my presentation. All right, to hide these controls, I'm going to hide myself. Okay, great. Well, thanks for having me on to talk a little bit about some of the research I've been involved in. I'm going to focus on a couple of papers that we've published the last few years that really look at each side of what geophysics offers in understanding glacial processes. The first half of the talk, we're going to focus on glacier seismicity. And so this is using geophysical signals generated by a process to understand that process. And then the second half is the other kind of traditional type of geophysics we do, where we use geophysical signals to generate an image of the subsurface. So they're going to be very different, but very complementary examples of how we're using geophysics to understand glacial environments and processes. Okay, and so first, all this work that you're going to see today has been funded by the NSF. And the NSF provides really great logistical support in the Antarctic. Numerous organizations. What you see here on the left is a C-130 landing on a completely unprepared piece of snow in the middle of an Antarctic ice sheet, which is still pretty amazing. And then we get a lot of our geophysical equipment from NSF-sponsored facilities, and of course, many people from the logistics side, students. Hundreds of people have really been involved in this. When you think about all the effort it takes to get work done in the Antarctic. So way more people than could ever be listed on an author list. Okay. And so we're going to be focused on Antarctica today. And a few years ago, the National Academies released a report, basically the strategic vision for NSF. What should we be studying in Antarctica? And here, priority one that they listed basically is how much and how fast will sea level rise. And basically, we need to really understand how we're going to get on with understanding change in the Antarctic cryosphere. And so this is really summarized in this nice figure I grabbed off of NASA's website, looking at basically mass change of the Antarctic ice sheet over the past few decades from the GRACE observations. On the left, what we have basically is mass loss in gigatons, and this is going from 2002 to about 2020. And basically, you see Antarctica is losing mass. Of course, that's very relevant, but what's also equally as important is when you look at the right panel, which is the spatial distribution of that mass change. You see the spatial pattern is very complicated, and this reflects a diversity of processes from basically snowfall patterns, how the ocean is interacting with the ice sheet, and that's what we're going to talk a little bit about today. So anyway, it's complicated, and the fundamental reason, again, that Antarctica is losing mass, and this differs from Greenland and a lot of the smaller ice caps, is essentially nearly 100% of the mass loss is because the glaciers are speeding up. It's not the ice sheet melting itself. Everywhere, especially down here, if we look in region 21 and 22, this is the Amazon Sea sector, which is blown up in this graph right here. Basically, these red colors basically show the ice flowing off of the continent faster. So to understand mass loss in Antarctica, we really need to understand the physics of glacier flow and all the processes that affect changes in glacier flow speed. Okay, so why is this, especially in this Amazon Sea area, why is the ice sheet speeding up and spitting out more ice into the oceans? Basically, warming oceans are melting the glacier, because especially a lot of wet Antarctica, in particular West Antarctica, is sitting on ground that's below sea level. And so it's in direct contact with the ocean, and that warming ocean is eroding the ice, causing retreat and causing it to accelerate. And so we really need to understand basically how ice gets eroded and breaks up where it meets the ocean, and we need to understand the response once it starts to get eroded and retreat. Okay. And so to understand this complicated process of how fast, how the oceans and the atmosphere interacting with the grounded ice, contributing to sea level, this is a document from the IPCC, and I won't go over this in detail. We all know where the IPCC documents live, but there's just this plethora of processes we need to understand. We need to understand the ocean. We need to understand fracturing of ice, material property. We need to understand sliding at the ice bed. We need to understand the atmosphere. So there's this real diversity of processes. It's much more complicated, especially when I'm giving a talk like this to a general earth science audience. People really think of ice sheets as a melting ice cube, and Antarctica is anything but a simple melting ice cube. And to understand this diversity of processes, I'm going to focus on some seismology and magnetotellurics today. But we really there's this range of tools, and it's really exciting to see how many different creative paths people are using to understand the changing ice sheets. We have satellites, we have ground-based geophysics, we have people on ships and helicopters and submarines, and it's just a real exciting time to be a part of the glaciological community. And we're making real big progress. But today I'm going to focus on two little vignettes that we've been recently published. The first half of the talk is that we're going to focus on calving from seismology, and we're going to also take advantage of some really spectacular remote sensing capabilities we have now, thanks to ESA and NASA, especially over the last few years. This was published a few years ago in GRL. And in the second half of the talk, we'll focus on looking at basically the subglacial boundary condition and how that might influence glacier sliding. And this, I only had a little teeny bit part in. There I am. Really, all the really clever stuff came from the first three co-authors, especially Chloe Gustafson, who got her PhD a few years ago at Columbia. All right, so that's what we're going to do. Okay, so first up, we're going to look at glacier seismicity and how we can study processes related to calving from seismic signals. So glacial seismicity is a rapidly evolving field. Rick Astor and I published a review paper a few years ago. It's now rapidly getting out of date as people really start to use seismic emissions from glacier processes to study the glacial environment. There's this whole host of glacial processes that produce seismic signals that allow us to interrogate those processes. It's never really the only tool, but it's another toolkit that people are using. We have fracturing from crevasses. We have water moving around under glaciers and ice sheets, which is really important. The turbulent flow can create seismic emissions. We have glaciers sliding. And what we're going to focus on here is down here at this CNL bit labels. We're going to focus on calving, the brittle failure of ice. Okay. And really a really motivating step forward in using seismic activity to study mass change happened about 20 years ago when Ekstrom and Nettles published the observation of these glacier earthquakes from Greenland. And this really changed how we looked at calving. So what we have here on the left is the traditional way, and still the most common way, and a very effective way, indispensable way of understanding glacier calving, was you look at a sequential set of satellite images. And what we have here on the right is a glacier calving front from Greenland. So it's really small. We're looking at a few kilometers by a few kilometers. In this case, the glacier is flowing from the bottom lower right-hand corner into the upper left-hand corner. So we have sea ice and glacier. And what the red line is documenting is the calving front in the first satellite image. And then later, they looked at a few days later, a second satellite image came by, a few days later probably. And this dashed red line is basically how much ice had calved between the two images. And that's really the best way to get and understand the spatial pattern of the calving process. But so this provides really high spatial resolution, but the physical process of calving happens in seconds. So we're really missing that temporal coverage. And so one way we can do that, and we're going to show next, is with, for some calving events, is seismic activity. And so what we have on the right now is a record section, as we would say in the seismic world. Basically, on the x-axis, we have time. So this is about, a half hour of seismic data for different seismic stations around Greenland. And what we have on the y-axis is we have these records of ground shaking sorted by distance from this calving front. And what we see here, this 1 and this 2, these big pulses of seismic energy that you see propagating away from the calving front are generated by the calving process. And they were actually able to pinpoint, where these events originated from using the seismic waves. So we know exactly when these calving events happen only from the seismic record. So that's a really powerful tool for understanding the timing of calving, because we might expect certain environmental factors such as sea swell, breakout of sea ice, things that happen at a resolution at a finer scale than satellite remote sensing can provide us. And so this is just another tool that we can use to understand the timing of calving processes. And just real quick, so basically the way these calving events can generate seismic energy, they can be recorded. I didn't know if I pointed that well enough. 600 kilometers away from the calving front, you can hear in this case, the calving event happening. So these are quite large. These are magnitude 4 or 5 seismic events. Is once you have, especially in these marine terminating glaciers with very narrow floating extensions, the icebergs that are generated are very tall and narrow, and they're unstable, and so they want to rotate. And when they rotate, they hit the front of the glacier, and that process generates seismic energy that can be transmitted and recorded hundreds of kilometers away. Okay, and why this is useful is this: we can record, we can invert the force history from a seismogram, so we actually can understand the process, what's happening. Then we can use a model and model the forces and compare that to our observations, and we can actually start to understand some of the physical processes of how the calving is actually happening at this sort of second time scale that we can observe with remote sensing. Okay, so one of the puzzling things for some of us is that these calving events these glacial earthquakes were most readily observed in Greenland. And so here's a sort of relatively recent study where they found 145 of these glacial events in Greenland over a 3-year period. But when we look to the southern hemisphere and we look to the Antarctic continent, the most sort of exhaustive survey of trying to find these types of events in Antarctica found 17 events in 12 years. So there's a large discrepancy between the productivity of these kind of glacial earthquakes in Greenland versus Antarctica. And there are a couple of reasons for that. The first of which is probably the dominant reason why we see so few of these events in the Antarctic continent is that the calving style. Antarctica is in contrast to Greenland, where a lot of the glaciers, the marine terminating glaciers, have very small floating extensions, so they can produce these basically buoyantly unstable icebergs. And Antarctica is fringed by large floating extensions, these large ice shelves. And basically what happens is when it produces icebergs, they're narrow and wide, and these tabular icebergs will just typically, once they break off, they just float away. They don't have a mechanism to generate seismic energy that can be transmitted into the solid earth. And then another factor is, compared to the northern hemisphere, there's just way fewer seismic stations in the southern hemisphere, and in particular, the Antarctic continent. So over the past 15 years, we've been deploying an increasing array of seismic observations. So this map that we're seeing here is basically a map of a lot of joint GPS and seismic observations that have been installed in the Antarctic continent since 2007. If we looked at this map in 2007, you would have just had a handful of stations. Now these seismic stations, GPS stations, weren't installed to study glacier seismicity. They're primarily installed to study the solid structure and how that influences the ice sheet. But we're also recording cryospheric signals. And so we started looking through this data, processing it, and sure enough, with this enhanced seismic coverage, we did start to notice some of these sort of glacial earthquakes, or these signals that looked a lot like events that were observed in Greenland. And now we're just going to focus on sort of one short time period, about an hour, of generation of these seismic signals that look a lot like Greenland. We're going to try and determine if these really are glacial earthquakes. Okay, so and now we're just going to zoom in on this red blocks for a second, just to show you the difference. Even if you're not a seismologist, I think everybody can see the difference between the seismograms on the left and the seismograms on the right. And so basically, again, what we're looking at is a record section of a seismic event, two seismic events. So we have time on the bottom, about a half hour in each record, and basically each one of these wiggly lines is a seismic signal recorded at a station in Antarctica, sorted by distance from the source. And basically what you see is this really weird seismic magnitude 3 event. It's really low frequency compared to like a typical earthquake, right? I think we can just see these are very different frequency contents, very different processes. So this thing on the left, which we're going to focus on now, is definitely not a tectonic earthquake. And now everybody should be able to go scroll through seismic records and pick out a glacial earthquake from a tectonic earthquake. You don't have to do anything too clever. Okay, so we have these things. They look like glacier events that we observe in Greenland. We're really excited because these things are really rare in Antarctica before now, and this is going to provide a new way to study calving in Antarctica. So the first thing we do is we, of course, use these relative arrival times to locate the event. And what's interesting is these two pair of events both originate from about the same spot. We're looking at mostly here, just West Antarctica. South Pole is kind of over here. They're occurring from this area of rapid ice loss in the Amazon Sea near the margin of the Thwaites Glacier, the largest single contributor to sea level from Antarctica. So that's pretty exciting. And so now we're going to zoom in on Thwaites Glacier. Now we've zoomed in onto a slightly smaller Hotzenstep of Antarctica. We're looking at a few hundred kilometers by a few hundred kilometers. So this glacier is quite large. And just to get ourselves oriented, so basically ice is flowing from right to left. We have Thwaites Glacier over here and the Amundsen Sea over here. So this is the ocean. And we see a very complicated margin of the Thwaites Glacier. At the top here, we have an ice shelf. So that's the floating extension. It's pinned on a little island right here. As we go towards the grid south, as we would say in Antarctica, down here, we have an ice tongue. Now, ice tongue is another floating extension, but it's not pinned up on anything. So it can't provide any back pressure to the glacier. And then down here at this sort of grid south margin of the glacier, what we see is a completely different style calving, basically where there's very minimal floating extension. This is very similar to the glaciers in Greenland. So across this, very wide, 100-kilometer-ish wide margin of the Thwaites Glacier, which is the largest contributor to sea level from Antarctica, we have this very diverse set of interactions with the ocean. We go from an ice shelf to an ice tongue to basically no floating extension or very minimal flow extension, which is very similar to the Greenland glaciers. And we're going to look at some really high resolution satellite imagery now. Because while in Greenland, these glacial earthquakes generated by calving are very significant, we also did some work where you can generate very similar signals from glacier slip. So we just wanted to confirm that even though they're occurring near the margin of the glacier, we want to do basically the limitations of the location. We want to get some other evidence to show that these are really due to glacier calving. And so to do that, so this is the same satellite image from the previous slide up now on the left, and we're just going to now even zoom in again. So we're really zooming in on the West Antarctic ice sheet here in that little red box. And we're going to look for additional constraints on what can produce these weird seismic signals, which are not earthquakes. And so what we have at the bottom here, I'm going to have this for a few slides. This is the seismic record of ground shaking at a single station about 125 kilometers away from the calving front, located right here, instead of looking at a sequence of seismograms. All right. Okay. And so we got really lucky with this seismic event in that there was a really rich set of satellite images that we could take advantage of. And so now, so once again, we're looking in this red box. This is about a day before the origin of these large seismic calving events. And what you can see here is we have, once again, on the right side of the page, we have ice sheet. And here we have the remnants of past calving events. We have sea ice, iceberg, bergy bits, and we have these cracks forming right at the boundary of basically ocean and ice. And so then if we go now, and this is what's phenomenal, we have a satellite image 10 minutes before our first seismic event. This is totally luck. You can't count on these repeat times. These images are usually several days. And so what we can see, if we rotate back and forth from these radar, these sentinel images, we can see a calving event has already begun. Basically, oh, pardon, see if I can kill that phone real quick. All right. Zooms from home. Okay, so what we can see is that what we have is a calving event has started. We still haven't seen our first seismic event. And remember, what we talked about is what so far has happened in the first 10 minutes of these of this calving event is we basically have generated tabular icebergs. So that's what these things here are. They haven't flipped over, but then if we look at these red dots, we got really lucky and we have another really great satellite image from about a half hour later, because Sentinel-1 used to have 2 tandem satellites. And what we'll notice is in that hour, we've generated these icebergs here and here. And what's distinctive about these icebergs is you can tell that they have capsized, because the reason these icebergs here and here are black is because that is the darker reflection from ice. This wider reflection basically is the snow surface. So it's really easy to distinguish between basically these tabular and these capsized icebergs. So we feel pretty good that we really are recording these glacier events similar to what we observe in Greenland. Okay, so there it is, capsized iceberg. So we're seeing what we see in Greenland. Okay, so now we haven't gone much further, but this is now opening up opportunities to understand calving on Thwaites Glacier, because now we have a really long track record of seismic data. Okay, and now real quickly, so that was these really large events that we can observe, hundreds of kilometers away. But by far, the most prevalent source of seismic activity on glaciers is cracking, small scale cracking that might generate sort of say magnitude 1, 2, -1 events. And so this is just an example real quick from work a few years ago on the Amory ice shelf, which is on the other side of the continent. But basically, this up high is a satellite image showing a rift propagating into this ice shelf. And at the very tip of this crack, all these little blue dots are very small seismic events. And you can actually track the propagation of this fracture with seismic activity. And so we wanted to see, all right, so we have these really large calving events. Can we actually see anything precursory or anything leading up to this large calving event? Okay, so now what we've done is, again, this is a seismogram. This is filtered at 1 to 5 hertz. This is the high frequency component of the ground shaking record. And once again, instead of looking at about an hour, a really short time period, we're looking at about a week of seismic data. And what we have here on the far right, November 8th, this is when that big calving event happened that we just looked at both in the seismic record and the satellite image record happened. But what you can see is we have all these really spiky little things. And what these are individual seismic events. And what's important here is if we count those events, this is now that same seismogram. And what we have in this blue line here, going from November 2nd to November 8th, when the seismic event happened, we have this accelerating rate of basically high frequency seismic activity. So now we want to look at, once again, because these events aren't recorded, they're much smaller, so we can't really locate them very well because we usually only record them at one station, the closest station. So we're going to look once again to the satellite record and see if we can get some clues to figure out what's actually happening with this sort of what looks like a precursory sort of seismic signal to help us understand the ultimate failure process. And once again, we got really lucky. And this time we're going to use optical satellite imagery, which is tricky because it's covered by clouds, but really provides a really nice resolution image of the calving frame. So once again, we're basically in that same little square we were before, really kilometer by kilometer area to really understand the physical processes that's leading up to this calving event. And so here we are, we're on October 30th of 2018. We're about a week a little more than a week before the ultimate large calving event. And what you can see here, I've marked as F1. So here's what's eventually going to become a large tabular iceberg. And so here's the open ocean down here just below that F1, and the far right-hand side is the grounded ice. And we see there's something there. There's already a fracture there that looks like it seems to be cutting across from this open ocean into this big rift here. And then we got another great Landsat 8 image on November 2nd, denoted by this red bar here. And what you can see is that F1, if we just slip back and forth, you can see that fracture growing. All right, and so our next high quality satellite image happens about a day before the ultimate large scale calving event. And what we can see now is we've had this fracture we've been showing in the first few slides has progressed even more. And we have this other crack here that's cutting across between a couple of rifts. We actually see this large rift propagating up off the screen. So if we just look at that slide back and forth, we can see, so what we think is going on is all these small seismic events we're recording the seismic signal associated with this preparatory, this accelerating failure of this very small floating extension that precedes this large calving event. And then here's a day after the calving event. Again, we see these tabular icebergs have moved away. We have these right here with my mouse. We can see these capsizing icebergs, which were responsible for helping to generate the large event that we can observe 600 kilometers away. All right. So we have these observations of accelerating deformation prior to this catastrophic failure, and there sort of is hopes that maybe we can use that to sort of understand the fundamental physics of calving in this area. Okay, so just to summarize this first part, Thwaites Glacier can generate these very large calving events. It's going to be recorded 1,600 kilometers away, really far. So I mean, this is and we see this multiple times. This is another calving event from April of 2017, which also produces one of these seismic signals. But again, here we can record the seismic signal at South Pole, which is pretty amazing. And again, we see this accelerating rate of deformation leading up to these large calving events. And again, here's another example of this. We have high frequency, lots of fracturing going on before we get to this basically catastrophic failure, which is when basically the seismogram almost saturates, and then after it goes back to quiet. So okay. So that's a recent study looking at sort of basically brittle failure processes, calving. Okay. Now we want to move on to the landward side of the system. So this is completely different. So basically, there's seismic activity being used to study failure processes that basically some help regulate the retreat of the calving front. But when we have this retreat of the calving front, we change the geometry. The next step is to understand how the glacier is going to respond, the grounded ice. How is it going to accelerate? And a big part of that, there are many things that control that. There's the topography plays an important role. And another really critical role is understanding the water system at the ice sheet bed interface, because it's that water that's going to allow the glacier to move fast. So just really quickly to review that, the bottoms of ice sheets are really wet places. The ice sheet, that water comes from two primary sources. We're trapping geothermal heat, and then the ice sliding over the bed. The friction will also melt, and how much melt? We're talking about millimeters per year is kind of the scale you should keep in your head. So these aren't vast quantities of melt, but millimeters, few millimeters a year of melt per year. And then we were able to generate rivers and lakes, sort of like highlighted here. Lake Vostok, has the volume of a Great Lake in North America, but it's buried under 3 kilometers of ice. Okay, and then once you start to pull and collect all of this water, right? Basically, this water especially when it mixes with dirt and till, it makes a slurry, very low shear strength, and basically that allows these ice streams like Thwaites to essentially slide over the bed. Internal deformation in many places of these fast-moving ice streams plays a relatively insignificant part in the total flux into the ocean. So we got water, it meets with dirt and lubricates the bed, and that's how these ice streams are moving fast. So what we really need to understand then, one of the things we need to understand is basically where is their sediment and where is their wet sediment, and what is the water budget. Those are three fundamental things, and we're gonna and geophysics provides one way to do that. Okay, so again, and so a relatively new way to do that. And again, so if you have any MT questions, drive over to Lamont, ask Carrie, or email Chloe. This was not my part of the work, but it's a really exciting new way that's really starting to be exploited to map the subglacial environment in Antarctica and elsewhere. But basically, we're using the natural variations in electric fields to map and magnetic fields to map resistivity structure with depth. And this has potential to map both sediments and water. And so Chloe, Carrie, and Matt did the first one of these surveys aimed at studying the subglacial environment. Surveys had been done to study sort of deeper crustal structure before, but to really understand the sort of tens to hundreds of meters below an ice stream was done a few years ago. And they went to this place right here. This is a map of ice sheet velocity of all of Antarctica. So it really shows these ice streams and how they're very, they look like rivers. So before we were looking over here at Thwaites, which is the one that's accelerating. And now we're over here on the Willans ice stream. It's not accelerating ice stream, but a lot of work's been done. And it's relatively easy to get to. So the main US base for Antarctica, McMurdo, is right here. So it's been studied for quite some time. And so they did this survey to look for sediments and water beneath this ice stream. Okay, and so basically, like I was saying, what you can do with this MT method is the fundamental observation product that you get is something like this on the left, which is resistivity versus depth. And in this case, what you see up here at the top, there's about 1 kilometer of ice in this part of Antarctica. And then what was found was this really low resistivity material, which has to be, when you apply some rock physics to it, basically has to be about 1 kilometer. So now on the right-hand side of the page, we've zoomed in. We go from 0 below the ice base to about 1 kilometer below the ice base, a little more than 1 kilometer below the ice base. But essentially, these black lines outline basically what this material needs to be, and it needs to be a relatively salty sediment, sedimentary basin. Okay. And so that was really great, but because this MT measurements are very labor intensive, basically these MT measurements were made over sort of 2 relatively small footprints. And so that's basically where I came in. And so and this really shows the value of adding a second geophysical measurement. And we had deployed some seismic instruments for another experiment in this part of the world some time ago. And one of the things you can do with seismic measurements, so before seismic instruments, before we were studying processes with the seismic instruments, but of course the other thing you can do is record earthquakes and then use those earthquakes to record and recover structure beneath the earth. And real quickly, it's what happens is basically when you have ice and sediment, the reverberations that occur because of these very large density contrasts produce very distinctive seismograms. So basically, this is just 20 seconds just to show you what another seismogram. Basically, these are called receiver functions, but essentially they're seismograms. But basically, here's an observation from one of our stations near where the MT stations were recorded. But basically, what we have at the top, middle, and bottom are basically different synthetic seismograms to try and match the observation. And so basically in blue would be if there was no ice. That's what your seismogram would look like. In red, if you just had ice sitting on crust, bedrock, and there was no soft sediment under the site, you would get something that looks like this orange seismogram. But this yellow seismogram is what you get when you have ice sitting on top of 1 kilometer of sediment and then a crustal structure. And so you can see that this yellow and purple match much better. So this allows us to say, there's a thick sedimentary basin in this area. And so now if we go back and look at this in map view, we've zoomed in again on this Willans ice stream. We're in this little box here, and the background image is color. So you can see this is the ice stream flowing from the upper left-hand to the bottom right-hand part of the map. So we have the Ross Ice Shelf down here. And so the MT surveys, which found this salty sediment layer, about 1 kilometer sedimentary basin, was done in this B box and this box C. And all the little circles there are places where we put out these seismic instruments. So we're able to connect these two regions and really make the case that these aren't localized pockets of salty sediments, but we probably have a very large scale, spatially extensive sediment system that's filled with salty water, and which we couldn't really say with, the seismic data is very good at saying there's sediments there, but not so good about so basically the content of the fluid content. So this is really nice to see these two things come together. Okay, so real quick, so where did the salty water come from? One possibility is essentially after the last glacial maximum, when the Western Antarctic ice sheet extended out towards the edge of the continental margin, it started to retreat as we came into the Holocene. And basically, the potential is that you basically get this, due to a glaciological adjustment, basically the ice sheet can go back farther than it is now. And then basically after you've unloaded the ice, the solid earth rebounds and the ice sheet will re-advance. And during this time, when the ice sheet has retreated, seawater comes in and infiltrates into these sedimentary basins. And that's why we have salty water, is that where the ice meets the ocean now is not the most retreated it's been. Okay, so that's how we get the salty water. Okay, so that's interesting. But what's the reason, one of the reasons this is most significant is what we look at when we look at the depth profile of the salinity curve. So again, 0 here on the left is the bottom of the ice sheet. And we're going down 1 kilometer below the bottom of the ice sheet. And these black lines now are the salinity curves. And what we notice, especially if you focus on from the 600 to up, is we see that the water is getting fresher as you go towards the ice bottom. And what does that mean? Well, if we had this ice sheet retreat, we had salty water come in, fill this cavity, infiltrate into the sediments. If there was no communication between the bottom of the ice sheet and this basically this saturated groundwater system of salty water, we would expect to see the entire depth be salty water. What we see is it's actually freshening upwards to the ice bottom. We talked about the bottom of ice sheets are wet places. We're producing melt millimeters per year. So what this tells us is that we actually have communication with this shallow hydrologic system that is driven by ice sheet melt with this deeper hydrologic paleo seawater system. So, okay, so this is important because most at present day, potentially important, most ice sheet hydrologic models only incorporate a shallow hydrologic system. By shallow, we mean tens of, at most, maybe like 10 meters. And so this is a diagram that Chloe put together. Basically, as we go from left to right, we're going down glacier. The glacier in this case would be flowing. And, so in this shallow system, we haven't talked about this today there much, but there's rivers, there's lakes and everything. We're melting millimeters of water a year. But now we have the first evidence that we have this salty deep water system that's talking to the shallow system. Okay, so and why does that matter? Okay, we're just going to walk through this very idealized numerical experiment for a second to explain why having groundwater talk to this shallow hydrologic water system may be important. And in this experiment, on the y-axis, on the x-axis, we're just going to look at 20,000 years of a very simple ice sheet simulation. And basically, on the y-axis, we have flux, a modeled flux of water going into and out of a groundwater system beneath an ice sheet. And of course, the different colors are basically just choosing different hydromechanical parameters of the sediment. And we won't focus too much on that right now. But basically, over the first 10,000 years of the simulation, basically the ice sheet is growing. And so what happens during this growth, you're increasing the thickness of the ice sheet, and that's applying more pressure, which drives water into the groundwater system. So that's a positive feedback, right? Because you're basically taking water away from the ice bed where it can't help sliding, which would sort of promote basically faster flow to the ocean. And so you're actually promoting growth. And what happens at 10,000 years in the simulation is it's a controlled retreat. We start thinning the ice sheet. And when you take that load off the ice sheet, what's it's going to do is that water is going to want to flow towards the ice bottom. That's positive in this case. And as you allow this water to come up to the base of the ice sheet, you're providing an additional source of lubrication and maybe helping the glacier flow faster. Okay, so that is the sort of one slide summary of why this may be an important process. Of course, we have to understand the mechanical properties of these sediments better. But that is one way this could happen. And so you can see this paper by Gooch, or there's a recent paper by Lee in Nature Geoscience, which we're going to look at next as well, where they discuss this in some more detail. And so the final sort of slide here is what we have here on the left is, so we focused on this one little small part of Antarctica in our, where we looked at the MT and the seismic and found this salty groundwater system that appears to be interacting with the bed of the ice stream. But what happened, what Lee et al. Did in this Nature Geoscience paper from a few months ago said, all right, we don't have perfect geophysics everywhere. Let's take what we have and throw it at some machine learning and see if we can come up with a probability of where we think these deep sedimentary marine basins may be. And basically everywhere it's red, they say there's a high probability of these sedimentary basins and the potential for these groundwater ice sheet feedbacks. And so you see there's a lot of regions in red. This is not a perfect map. The data is very sparse. I know there are a few places in here where some data is coming online that wasn't incorporated in this, and this is going to need to be updated. But the point being, it's a good first attempt to say, look, there's probably sedimentary basins everywhere, and we could this could be an important process, not just for where we studied, but for the entire continent or large portions of the continent. So basically, red, there's sediments, blue, probably not. Okay, so this is my final slide, same one I showed it before. Basically, we've really focused on just two really small nuggets of the story, but there's a lot of processes that we're going to need to understand if we're going to be able to forecast the future of the Antarctic ice sheet with increased confidence. And it's really exciting. We got lots of smart people tackling all of this diversity problem with a lot of really interesting tools, and geophysics is just one of those. So thank you.
Thanks, Paul. That was quite interesting. We had a question from Laurie Padman in the chat.
Okay.
Question is, what sets the length scales of the small tabular icebergs calving from Thwaites?
Oh, that's a very good question, because it's very that I've looked at some of the satellite imagery, and there's definitely this part of Thwaites that has either an ice shelf or tongue. It only gets a few kilometers away, that progresses, and then it produces these tabular, these sort of hybrid calving events with both hybrid calving events where you get both these tabular icebergs and these capsizing icebergs. And I don't know what sets that length scale. I suspect it has something to do, somebody on the Zoom might have better insight. I suspect it has something to do with the ice thickness. The ice here is still, I don't know, it's like a kilometer thick, I think. I can't remember. Oh, I should have checked that. But yeah, almost certainly I think would have something to do with the ice thickness, but I'm not sure. That's speculating.
So you don't think it's got something to do with some periodicity in the coursing? It's not an annual variability of lubrication or something else?
I haven't, you're right. So velocity probably also matters in there too, because it's going to affect strain rate. I haven't thought about that in quite a while. I did look for some seasonal signal, and I need to go back and look at this because when I was working on this, we didn't have all the seismic, because we didn't have all the seismic data back yet for all of this network, just due to logistical problems. And so I keep meaning to go back and, looking at a catalog much more aggressively, but intently. But the best I can tell right now, I may change this, my opinion of this, but there doesn't appear to be a seasonal cycle, because I started looking for, maybe there's a melange signal in there or a sea ice signal, and I just need to go back and look a bit harder. How's that for a non-answer? Yeah.
As a non-answer, it's pretty good, I guess.
Okay. Okay.
Do we have any other questions, Paul? Okay, Jeff has a question. Does the seismic shock from Greenland iceberg calving cause a cascade of calving?
Let me think. Not that I'm aware of. I mean, you definitely can get very complicated signal, multiple events occurring in very short durations, but I don't think anybody, the best of my knowledge, I think the question is basically, do you get one calving event and you get a chain reaction? I think and I don't know of that, because essentially at some point, basically you calve and then you get back to basically less deformed ice. And so you have to wait for things to progress a little bit more. And because basically the calving, right near the calving front, you have these really high strain rates. And so things are really deformed. And once you get rid of that, you have to wait a little longer for that new calving or new terminus to get deformed enough to break off. That's my understanding. But again, I'm a seismologist.
Well, at that particular point, right? So if you had a calving event that was only a fraction of the ice front, then that calving event might release or change the strain field so that the next part of the ice front's now more susceptible.
Yeah, right. I mean, I guess, it definitely, right. Because especially in that figure I showed from Kira Olson's paper, right? Definitely, it seems like the one part broke off and then the next part broke off because of just what Lori said. Yeah, definitely. But definitely small. I guess it depends the size of the cascade you're interested in. Yeah, definitely. Yeah.
Can I ask a different question?
Okay.
In Chloe's paper, I think you were showing that the saturated sediment is very saline.
Correct.
So when you get this change in ice loading so that you're wicking water up or down through that sediment, does the salinity matter or just the liquid? Because can you change the salinity of the till layer underneath, and what does that do to freezing point?
Yeah, I think that's really, because I think I didn't talk about it here, but I think definitely the sort of people who care about critters living under ice sheets and life and things are very interested in basically, because that was we talked about it a little bit in the paper, but that's another interesting thing, is basically this exchange is bringing up nutrients and things that critters like to eat on. But I think that's definitely something to think about, is, basically how does, freezing point, salinity, salinity definitely changes freezing point, but we haven't really explored that, but I think it's definitely something worth thinking about.
Any other questions? Actually, I had a question about the seismic measurements. So do the seismometers have to be on the ice to make these measurements, or can you have?
No, it's a very so a lot of the so for the first part of the story, some of those were not on the ice at all, they were on bedrock. And the second part, where you're trying to image basically subglacial structure, sediment structure, there are other techniques. So the technique we use, we're sitting right on top. We're basically doing a 1D measurement right below the seismometer, which is preferable, but often challenging. But you can totally use more distant stations. Basically, you do a tomography, basically, right? If you're surrounding your area of interest, you can do tomography and use basically crossing paths from more distant station. I mean, definitely you want to be on if you're doing Antarctica, you definitely want to be Antarctica, and you can make things, but it's a kind of, you'll generate kind of a relatively blurry image, which,
Interesting. And maybe one more question. Can you distinguish between like different types of events, like just by looking at the seismic data?
Yeah, it's really amazing. Like the past. So when I started grad school, like what, 2001, you know, if you look at the number of papers that were on glacier seismicity, there was like, well, there's my PhD advisor, and there was like, you know, a handful. I mean, there was good. I mean, it was a few dozen. But now we're really, thanks to work from a lot of people, yeah, we're really starting to learn. Yeah, just from looking at the seismogram, you can really get a sense of, because basically an event from cracking, I didn't really show you, but you know, basically, if you want to understand even tabular iceberg formation, those kinds of events produce very distinctive seismic waves. In alpine environments, especially, it's really been exploited where you have moulins taking surface melt from the surface and in Greenland into the base of the ice sheet. This water flowing around, basically you have turbulent flux, and basically water bouncing around and hitting the ice generates seismic waves, and you get this kind of tremor signal. And so you can monitor, basically from a seismogram, you can monitor how much water is flowing in and under the glacier and relate that to the glacier's basically change in flow speeds. So there's this whole, yeah, for each, I showed that basically an overview diagram for basically, you know, every process basically has a very distinctive shape of the seismogram, which is very different from what seismologists studying, you know, earthquakes have been studying for, you know, a little over 100 years, modern seismology, I guess.
Anybody else? Okay, well, I guess we can wrap it up for today. So thanks again, Paul. Thanks for coming.
Great, thanks.